and we said that this area over here, ये जो यहाँ पे बना हुआ है, ये part वो है which is called the colloidal domain, and it is from 1 nanometer up to 1 microns. But we also said that the colloidal definition is basically due to the phenomena. That is, when a colloid is formed, there is and this is something which coincides with the properties of the surfaces also. The surfaces have a lot of different properties, and we will come around this when we progress in the course, that the surfaces have different properties. So surface is that area of the bulk which is the first part of the material which come in contact with its environment. ठीक है? So that's why the surfaces are important, because they are the first point of contact with the environment. And the energy of the surface is very much different from that of its bulk. This is also something that we know. There are several examples of that. Probably we will come across a cartoon of that when we progress in the course. So anyway, the colloid therefore is also a kind of manifestation of an increased surface area. ठीक है ना, colloid में भी ऐसा ही होता है, because what we are looking at that, for example, we have a bulk material, and then we divide that bulk material into small pieces, and then those small pieces obviously have a greater representative surface. So if you have a material, you divide it, you are actually increasing its surface area. So in a way, colloid is a manifestation of increased surface area. So when a colloid is formed, more and more of the surface become in contact with the environment. More and more of the material become surface. ठीक है? तो आप मटेरियल को डिवाइड करते जाते हैं, और वो जो मटेरियल होता है, it continues to be converted into a surface. ठीक है ना? So if we look at the definition of colloid, so we see that the colloidal system have a minimum of 2 components. So let's say we have colloidal dispersions, then they are system of particles or droplets. Particles mean that you are referring to solid materials. So in that case, you will have particles. Droplets mean that you are referring to liquid materials. So for particles, you can have a dispersion of, let's say, nanoparticles or biological particles. For droplets, you can have dispersions of oils in water or water in oils. So both of these systems can be colloids, in which either the particles are dispersed somewhere or droplets are dispersed somewhere. So if we have the right dimension for the dispersed phase, and then we have a dispersion medium, for example, gas, liquid, or solid, then we will call it a colloid. But obviously, if the properties are changing, then we will still call it a colloid. So the medium is called the continuous phase. That is the medium which is present in excess. But the other one, which is present in smaller amount, but obviously the surface area is large, the particle size or the size is small, that is called the dispersed phase. ठीक है ना? So the medium is called the continuous phase, which is usually in excess, but which are the right dimension. The particles or droplet have dimensions, or one key dimension between 1 nanometer and 1 micrometer, and their special properties arise from the large surface due to precisely these dimensions. As we saw earlier, this figure refers to the last figure that we just discussed. However, sometimes even larger particles, where the dimensions are larger, that is up to 10 or even up to 50 micrometers. For example, in case of emulsions, or very small particle, for example, 5 into 10 dash power minus 10, what does it mean? That we are looking at 5 angstrom can present colloidal character. Thus, despite the above definition, that is the definition of size of 1 nanometer to 1 micrometer, if something look and act like colloid, then it will be a colloid. So this is what I was talking about, that although we refer to a size domain, but if something behave like a colloid, that is, it shows the phenomena, the colloidal phenomena, then it will still be called a colloidal material. ठीक है ना? So we see that Thomas Graham in 1805 to 1869, who is the pioneer in the study of colloidal system, used the term colloids derived from the Greek word for glue, which is colla. He thought that their special properties were due to the nature of the compounds involved. Later, it was realized that the size of the particles of the dispersed phase, as we call it, is solely responsible for the special properties of the colloidal system. And today we know that when the size of the particles is reduced, the surface area increases, and surfaces, when increases, are really important and they show a lot of different properties. Now, you may be aware that the different surfaces are also different in properties, because we know that if a surface or if a solid material is cut in a certain direction, it will give you a certain type of surface. If it is cut in a different direction, it will give you a different type of surface. One direction will give you a catalytic surface, and the other direction will give you just a simple surface. It will not be catalytic. So means one cut of the surface have certain properties while the other cut doesn't have those properties. So surfaces are important, and the colloidal phenomena is kind of the manifestation of those properties. So it happened earlier when people were not aware of these things, that if the particle size is reduced, then you are going to get a certain type of um, properties out of that. So if the property is there, that material was termed as colloid or colloidal material. Okay. So I hope that you understand this thing. So let's move forward. We have different shapes for colloids. If we look at here, uh, so here we have, if we want to know about the shape of the colloids, we first of all we look at a simple example. Water is non-colloidal. Okay. And then we have milk, which is a colloidal system. So milk is basically an emulsion. Water is just a solvent. So you can see that the two of them are different in their color. One is white and the other is transparent. So this is basically opaque. So if you have an emulsion, then most of the time the emulsions, the majority of the times will be white in color. That is, whenever you have an emulsion, emulsion is what it is when you have oil dispersed in water or droplets of oil dispersed in water. So water is acting as a medium and the oil is acting as a dispersed phase. So if you have that kind of thing, then that will be emulsion. And there you will see that the color of the emulsion is white. So white color is a manifestation of formation of emulsion. But if you have a transparent type of liquid, then it is most probably solvent. So how to recognize them and what is crucial? Many colloidal systems like milk are easily identified by their color. As I told you that the color is white. Most of the time it will be white, or more precisely their non-transparent appearance, as in the case of, again, in the case of milk, where it is opaque. So the optical properties of colloids are very important. Also their characterization and study of their stability, that we will see in later lectures. So different shapes of collided particles with molecular weights are provided here. You can see that we have spherical particles, and then we have something which is not spherical, and then we have these globulin, or we have a lipoprotein, albumin, and we have a rather very different structure over here. Not just that the shape of the particles, the colloidal particles are different, but their sizes are very much different. For example, if you compare this to this, there is a very large difference between them. There is a difference between the size, and there is a difference between the weight of them. So if this is 100 angstrom, you can see that this is a very large part which is covered over here. Okay. So is there any question so far? कोई सवाल तो नहीं है ना? Okay. We also had a discussion about this, a little bit of it. That is surfaces and interfaces. So colloidal systems are composed of small particles dispersed in medium. The fact that these particles have small dimension is the reason that a huge surface area is created, and that surface area is interfacial area. So their high interfacial area is the reason why colloidal systems have special properties, and also why we study colloids or interfaces together. As shown in the figure, the the surfaces or interfaces are sometimes considered to be simply dividing lines. So just if you look at here, this one is the solid. So we can see that the solid A is different from solid B. So when they are in contact, we have an interface over there, and this interface will be a solid interface, and this interface is basically a dividing line which is between the two phases. So although they are not real lines, they do have a certain thickness of a few angstrom, especially in the case of liquids, which is of the order of molecular diameter. So the surfaces and interfaces involving solids, liquid, and gases, an interface has a thick of a few angstrom. Yeah, if you look at here, this one is really, this can be a bit thicker, but in case of liquids, we see that it is in the range of angstroms. Now, what we see is that solid is in contact with liquid B, and liquid B is in contact of liquid A, and liquid A is in contact of gas. Now, liquid A is in contact of gas, therefore, this interface between liquid A and the gas is called the surface. And since this is a surface, therefore, the phenomena which is relevant to it will be surface tension. Now, liquid A is in contact with liquid B. For example, this is oil, and this oil is in contact with water. So again, there is an interface formation, but since both of them are liquids, we will call them a liquid-liquid interface, and the corresponding phenomena will be called interfacial tension. Now, the liquid B is in contact with a solid, and therefore this part is again an interface, and this is a solid-liquid interface, and the phenomena that we observe over here is the interfacial tension. So again, we have two type of phenomena observed. One is surface tension, and the other is interfacial tension. So whenever you have material in contact with a gas, so it can be liquid or solid, then we call it surface tension. But if there is something other than gas, then it will be called an interfacial tension. Okay? You understand that? So now we move to intermolecular forces around a molecule in the bulk and around a molecule in the surface to understand that why the surface is different from the bulk. Okay. पर अब हमारे पास we have this sort of cartoon and we have white circles and then we have a dark gray circle and then we have a light gray circle. So the light gray is the circle of these circles are for showing the surface. The white circles are showing number of bulk molecules and the gray one is just identified bulk molecule which is equally surrounded by white circle. So you can see that this gray molecule, dark gray molecule over here is surrounded in this direction, in this direction, in this direction, in all directions. You can see also that if you look at the cross areas, it is also surrounded like this. And you can imagine that if you imagine that in 3 dimension, then you can imagine that there will be a molecule which is above that and below that and on the sides and so on. If you look at this molecule again, this is the white above this one, the dark gray one. You can see that again, this is surrounded by molecules in all directions. So it means that whatever force is applied on this dark gray molecule is equally in all directions. But if you look at this one, which is on the top, which is on the surface, then it doesn't have any circle above it. Okay, so these light gray ones doesn't have any circles above them, which shows that there are no molecules above them, which naturally make it an imbalanced molecule in terms of energy. So you can see that if some molecule is present over the surface, then it is short of balancing forces. It is not the case if the molecule is present inside the bulk, where the molecule have is surrounded in all the डायरेक्शंस. ठीक है ना. तो यहाँ पर तो ये सारी तरफ से इसको उसने घेरा हुआ है मॉलिक्यूल्स ने, बट इफ यू लुक एट द सरफेस इट इज नॉट surrounded. Since it is not surrounded, therefore it will have an imbalance of forces. ठीक है. तो क्या होगा if force is applied downward on these light gray one by the white ones, if it is applied downward, it means that the surface is going to be pulled downward. If it is pulled downward, so there is also a force on the sides, because this, for example, this molecule is attracting on this side, this is on this side and so on. So it means that there is a pull downward and a pull on the side, so which make the surface stretched. Okay, so that's why the surface of liquids are stretched or they have surface tension. ठीक है ना. So this is why the surfaces are different. Similarly, if you have solid materials and they are exposed by removing the upper layer, then obviously those molecules are having imbalance of forces, and that imbalance of forces is making them energetic. So this is something what is happening over here. यहाँ पर कुछ नहीं है, ये वाली जगह पे this is empty, this is empty and this is empty. लेकिन इसको यहाँ पर अगर आप देखें तो still hold like this. ठीक है. So that's why you will see that there is a kind of net stretch over there. This thing is stretched. ठीक है. तो ये ऐसे होगा कि जैसे आप इसको ऐसे नीचे खींच रहे हो, तो अगर इसको आप नीचे खींच रहे हो तो ये चीज़ जो होगी ये इस तरफ को स्ट्रेच हो जाएगी. जैसे टेबल के ऊपर कपड़ा होता है ना, इफ़ यू हैव अ क्लॉथ ऑन द टेबल एंड यू पुल इट फ्रॉम वन साइड, तो क्या होता है दैट क्लॉथ बिकम अ बिट स्ट्रेच ऑन द टॉप, हालांकि यू आर पुलिंग इट डाउन हेयर. लेकिन जो स्ट्रेच होता है वो उसका इस तरफ फ्लो कर रहा होता है, यहाँ पे। इसको मैं कैसे करूँ, ये इस तरफ जा रहा होता है, ये सारा स्ट्रेच है उसका, वो ऐसे जा रहा होता है, ठीक है। यू अंडरस्टैंड दैट? तो वही बात समझ आ गई आप लोगों को?
जी सर।
यार हसीबुल्ला तुम्हें ही समझ आ
जी
रही है,
सर, आ
बाकी
रही
देखो
है।
किसी किसी को समझ नहीं आ रही है बाकी। है, ये क्या बनेगा? अच्छा, okay, so the question is that what is the thickness of the interface? And we just saw that the thickness of interface is few. The colloids are micro heterogeneous. So here we see that we have a vapor phase over here, we have a liquid phase over here, we have liquid phase over here. But this molecule is, as I explained earlier, this is light gray molecule, this is present over the surface. So these are the surface molecules, and where we have the bulk molecule. Both of them are different from each other. The surface molecules are energetic as compared to bulk molecules. So if you pull this molecule from here to the surface, you need to put some energy on this molecule to make it energetic, ठीक है ना? So we will see that what is the importance of these few angstrom thick surface, ठीक है, ये हमें देखना चाहिए that important, ठीक है. We have some examples of interfaces over here, which are well-known interfaces. For example, we have liquid surfaces, surfaces of ocean. Then we have solid surfaces, where we are looking at adhesion, glue, tapes. We have road surfaces, where we are looking at solid air or solid car tire interface. Then we have lung surface, which is uh, quite a natural phenomena, because in lungs there is a lot of exchange, there is gas exchange, there are surfactant involved, there is surface area involved. It is doing a big job. So lung surface, and then we have washing and cleaning, that is surfaces, foams. Then we have emulsions, in which we have cosmetics, pharmaceutical products. Then we have in different industries like oil and gas, paper, milk product, etc. Milk product में जैसे you have cheese, mayonnaise, and so many different type of spreads. So all of these are basically a manifestation of colloidal materials. And for example, a very important class in colloids is food hydrocolloids, and then there are other hydrocolloids which are related to this type of materials. Now, let's look at the forces on molecules at the surface and bulk. We just had a look at the diagram in the last few slides, where we were looking at the forces which were different in the bulk and on the surface. Here we have an explanation. So if we have the molecules at the interface, they would be under asymmetrical force field, which produces the so-called surface tension or interfacial tension. Now you can see that the surface tension is a lot different than interfacial tension, which is practically something that we observe. And obviously the reason is that in case of surface tension, you are looking at molecules, liquid molecules in contact with gas molecules. So if the gas is not absorbed over the top of the liquid, and there is a mismatch between the sizes or the forces in intermolecular forces, then obviously the result is very much different from interfacial tension, where the contact is between, for example, two liquid surfaces, two solid surfaces or a liquid and a solid surface. So what you get is a very different type of tension as compared to surface tension. So this leads to the adhesion forces between liquid and solid, which is a major application area of surface and solid. This is a very important thing that we just uh, discussed here, that molecules at the interface would be under an asymmetric force. हमने discuss किया, or why this is asymmetrical force, we also discussed that. So you have to remember that. This leads to the adhesion forces between liquid and solid, which is a major application area of the surface and colloidal science. The resultant force on molecules will vary with time because of the movement of molecules. Now, let's say if we are talking about liquid like water, the molecule at the surface will be pointed downward into the bulk phase. The nearer the molecule is to surface, the greater the magnitude of the force due to asymmetry. The region of asymmetry plays a very important role. Thus, when the surface area of liquid is increased, some molecule must move from the interior of the continuous phase to the interface. One thing that you first need to understand is that if you have a liquid and you have a molecule at the top, then that molecule has an equal probability of being present in the bulk. Yet, the molecule when present on the surface is very, very different from the one which is present inside the bulk. This is something that we just saw, that these two molecules are very much different from each other. Yet, as I said, that the molecule in the bulk have the same probability of being present on the surface, and the surface molecule have the same probability of being present inside the bulk when you are talking about the uh, for example, the pure liquid, if you are talking about a pure liquid. So now the thing is that since these two molecules are different from each other in terms of force, if you want to bring a molecule from the bulk to the top of the surface, then that will need some work to be performed on the bulk molecule. So what you are doing is that you are pulling a molecule from the bulk and you are pulling it to the top of the liquid. So that needs work. Similarly, uh, if you are pulling the molecule to the bulk, what does it mean? That the surface area of the liquid is increasing. This is how you add the molecule to the surface. If you add the molecules from the bulk to the top, then it will increase the surface area of the liquid. Okay. So these are some important points here. And you need to remember that. बात आपको समझ आ गई है ना? It's very important point. The surface tension of liquid is force acting normal to the surface per unit length of the interface, thus tending to reduce the surface area. The molecules in the liquid phase are surrounded by neighboring molecules, and these interact with each other in a symmetrical way. In the gas phase, where the density is 1000 times lesser than in the liquid phase, the interaction between the molecules are very weak as compared to those in the dense liquid phase. Thus, when we pass from liquid phase to the gas phase, there is a change in the density factor by 1000 times. This means that while in the liquid phase, a molecule occupies a volume that is 1000 times smaller than when it is in the gas phase. So obviously in gas phase, we have plenty of volume available. Okay? That the surface tension of liquid the surface tension of a liquid is the force acting normal to the surface per unit length of the interface, thus tending to reduce the surface area. The molecule in the liquid phase are surrounded by neighboring molecules, and these interact with. I have already explained this. So if we look at the surface tension is the differential change of free energy with a change in surface area. An increase in the surface area requires that molecules from the bulk phase are brought to the surface phase. This is valid when there are two fluids or a solid and a liquid, and it is usually designated as interfacial tension, bringing a molecule from bulk to the surface. And this is something that I just explained. So when these molecules are on the surface, they are attracted by the molecules below and by the lateral ones, but not towards the outside. The result is a force directed inside the liquid. In its turn, the cohesion among the molecules supplies a force tangential to the surface. So a fluid surface behaves like an elastic membrane that wraps and compresses the liquid below. The surface tension expresses the force with which the surface molecules attract each other. It is common observation that due to surface tension, it takes some effort for some bugs to climb out of the water and lakes. The examples are marsh striders, water striders, and so on. These are some of the examples. So here you see them. So this is a marsh strider, and this one is a water strider. Both of them, they basically use the phenomena of surface tension to float or maybe to actually to walk over the surface of water. You can see that their legs are quite long over here, and they are not pointed to break the surface. Same is true for this, which is also eating something. And then we have this needle which is floating over the surface of water. So we have this classification of colloids. We also saw that yesterday we have these different types of colloids present. Liquid gas, we have liquid aerosol. The example is fog, mist, liquid space. We have gas liquid. That is the dispersed phase is gas. The dispersion medium is liquid. We get a foam, and it is in the cream, shaving cream, etc. Then we have liquid in liquid. We get emulsion, where we have milk, mayonnaise, butter, etc. Then we have solid and liquid dispersion. We have toothpaste and paints. Then we have gas and solid, where we have solid foam, expanded polystyrene, etc. We have liquid and solid gel like purg. And then we have solid in solid, solid dispersion like pigmented plastic bones, etc. So it means that a colloid will be decided on the base of the dispersed state of the dispersed phase and dispersion medium, whether it is a gas, liquid, or solid. We also have association colloids, which are thermodynamically stable. We have lyophobic colloids, which are thermodynamically unstable. Then we have kinetically stable colloids, in which we have metastable states. And we also saw that the Faraday's colloid is basically example of kinetically stable colloid, where we input energy and make them stable. And the Faraday colloid of that is the dispersion of gold colloid is stable for more than 100 years. So technically, it is not that stable as compared to the other stable colloid, but you see that there are ways in which the kinetically stable colloids also remain stable for a very long time, and that can be something which can be achieved. So colloids or colloidal dispersion can be classified according to a state of the dispersed phase and the dispersion medium, gas, liquid, solid. We already saw that table. Or according to their stability, the most well-known colloids are emulsions, dispersions, forms, liquid and solids, and aerosols. The common colloidal dispersions are thermodynamically unstable, while association colloid, that is surfactants and polymer protein solutions, are thermodynamically stable. In addition, there can be multiple or complex colloids, which are combination of dispersion, emulsion, surfactant, polymer, and continuous phase, etc. Then we have network colloid, also called gels, and they are sometimes considered to be a separate category. And this is a very important category which are nowadays used for drug delivery. Then we have lyophobic colloids. Lyophobic colloids are those in which the dispersoid, that is the dispersed object, constitute a distinct phase, while lyophilic colloids refer to single-phase solution ions of macromolecules or polymers. Lyophobic colloids are thermodynamically unstable. So we have different terms here. We have terms hydrophobic, hydrophilic, lyophilic, and so on, which actually designate that what type of solvent we are considering, what type of material we are considering as a dispersed phase, and so on. So based on that, we are defining our colloids. So any question up to this point?